Welcome back. In the last video, I told you that pressure times volume is a constant, that if you increase the pressure, or if you increase the volume, you're going to decrease the pressure, and hopefully you got an intuitive sense why. Or likewise, if you squeezed the balloon or the box, and there were no openings there, then the pressure within the box would increase. So with that said, let's see if we can do a couple of fairly typical problems that you'll see. So let's say that I don't know, I have a box or a balloon or something, and let's say it has a volume. So let me call this the initial volume. Let me erase all of this. So let's say my initial volume is 50 cubic meters, and let's say my initial pressure is 500 pascals. And just so you remember, what's a pascal? That's 500 newtons per meter. 500 newtons per meter cubed. And then let's say that I take that box or balloon or whatever and I compress it down to 20 meters cubed. So let's say I compress it. So I squeeze it. So that was like the first example I gave last time. But it's the same container, and I squeeze it down to 20 meters cubed. What's going to be the new pressure? Well, you should immediately have an intuition that what happens when you squeeze a balloon? It becomes harder to do it. Sorry, I just had some peanuts. I should have had some water with it. My throat's very dry. But anyway, I'll try to soldier through this video. So what's going to be the new pressure? Well, it's definitely going to be higher, right? When you decrease the volume, the pressure increases. They're inversely related. So the pressure is going to go up. And let's see if we can calculate it. Well, we know that P1 times V1 is equal to some constant. And since we have no aggregate change in energy, right? I'm just telling you that the box squeezed. I'm not telling you whether it did any work or anything like that. The same constant is going to be equal to the new pressure times the new volume. It's going to be equal to P2 times V2. So you could just have the general relationship. P1 times V1 is equal to P2 times V2, assuming that no work was done and there was no exchange of energy from outside of the system. And in most of these cases, when you see this in exam, that is the case. So the old pressure was 500 pascals times 50 meters cubed. And one thing to keep in mind, because we're using both the same units on the same side, because this is an equivalent, this equivalence is not equal. We're not saying it has to equal to some necessary absolute number. For example, we don't know exactly what this K is, although we could figure it out right now. As long as you're using one unit for pressure on this side and one unit for volume on this side, you just have to use the same units. So we could have done this same exact problem the exact same way if instead of meters cubed, they said liters. And as long as we had liters here. You just have to make sure you're using the same units on both sides. So in this case, we have 500 pascals as a pressure. The volume is 50 meters cubed. And that's going to be equal, excuse me, to the new pressure, P2 times the new volume, 20 meters cubed. And so let's see what we can do. We can divide both sides by 10. So we can, just take a 10 out of there. And then we could divide both sides by 2. So that becomes a 250. And so we get 250 times 5 is equal to P2. And so P2 is equal to 1250 pascals. And if we kept with the units, you would have seen that. So when I decreased the volume by by roughly 60% is how much I decreased the volume, I have the pressure actually increased by 2.5. So that gels with what we talked about before. Now let's add another variable into this mix. Let's talk about temperature. And like pressure and like volume and like work and a lot of concepts that we talk about in physics, temperature is something that you probably are at least reasonably familiar with, right? Temperature. I mean, how do you view temperature? Temperature, I think if a high temperature means something is hot and a low temperature means something is cold. And I think that also gives you intuition that a higher temperature object has more energy, right? Higher temperature has higher energy, right? The sun has more energy than than an ice cube, right? I think that's fair enough. And I think you also have the sense that what would have more energy? A 100 degree, let me think of something. Cup of tea, or a 100 degree, I don't know, vat of barrel of tea. I want to make them equivalent in terms of what they're holding. So I think you have the sense, even though they're the same temperature, they're both pretty warm. Let's say this was 100 degrees Celsius, so they're both boiling. That the barrel, because there's more of it, it's going to have more energy, right? It's equally hot, and it's just there's just more molecules there. And so that's what temperature is. Temperature in general is a measure, roughly, is equal to some constant times the kinetic energy, the average kinetic energy per molecule. Sorry, it's the average kinetic energy per molecule. So the average kinetic energy of the system divided by the total number of molecules we have. So if I took, I guess another way we could talk about it is temperature is essentially energy per molecule. So something that has a lot of molecules, where n is the number of molecules, right? So another way we could view this is that the kinetic energy of the system is going to be equal to the number of molecules times the temperature. And this is just a constant, so if, times 1 over k, but 1 over k, we don't even know what this is, so we could say that's still a constant. So the kinetic energy of the system is going to be equal to some constant times the number of particles times temperature, right? And we don't know what this is, and we're going to figure this out later. So this is another interesting concept. We said that pressure times volume is proportional to the kinetic energy of the system. The aggregate, if you take all of the molecules and combine their kinetic energies, and these aren't the same k's. I mean, I could put another constant here. I call that k1. And we also know that the kinetic energy of the system is equal to some other constant, I don't know, times the number of molecules I have times the temperature, right? So if you think about it, you could also say that this is proportional to this, and this is proportional to this. So you could say that pressure times volume is proportional to the number, and these are all different proportional constants. We'll figure out this exact constant later. But we could say that pressure times volume is proportional to the number of molecules we have times temperature. And we said kind of temperature is we can kind of view it as energy per molecule. Or another way we could say it, if this constant is constant, which it is by definition, let me change the colors, and the number of molecules is constant, we have PV over temperature, pressure times volume over temperature, is going to be equal to something times the number of molecules. So we could say that's some other constant, I don't know, K4. So this is another interesting thing to think about. We said pressure times volume is equal to pressure times volume. Now we added temperature into the mix. So let me clear this up. I think I got my throat back. So we could say P1 times V1 times over T1 is equal to P2 times V2 over T2. And does this make sense to you? Let's say, what happens if I have another box, and I have my particles bouncing around like always, and they're have some volume and some amount of pressure. What happens when the temperature goes up? What am I saying? Well, I'm saying that the average kinetic energy per molecule is essentially going to go up. So they're going to bounce against the walls more. So if they bounce against the walls more, the pressure is going to go up, right? Assuming volume stays flat, right? Another way you could think about it, let's say the temperature goes up, and I increase, and let's say the pressure stays flat. So what did I have to do? Well, I just said if the temperature goes up, the average kinetic energy of each molecule, they'll bounce more. So in order to make them bounce against the sides of the walls as often, I'd have to increase the volume. So if you hold pressure constant, the only way you can do that is by increasing the volume while you increase the temperature. So let's keep this in mind, and we will use this to solve some pretty typical problems.